Page 4 of Transformations Addendum, the reciprocal of a function. For a function f of x, the reciprocal of the function is 1 over f of x. You notice that this is not the inverse function, which is expressed as f inverse x. That's the inverse function. The inverse function is not 1 over the function. It is, you do variable interchange, you switch the inputs and outputs to x's and y's, and you make kind of like a reverse function of the original function. The reciprocal function is simply putting 1 over the function. Okay. When you graph 1 over f of x instead of f of x, the zeros of y equals f of x become asymptotes of 1 over f of x, vertical asymptotes to be exact. Okay. The local maxima of y equals f of x become the minima of 1 over f of x. And when f of x is greater than 0, then 1 over f of x becomes, is greater than 0. And when f of x approaches 0, 1 over f of x approaches infinity, right? Because if you put a 0 in for f of x, it would be 1 over 0, which is approaching infinity. Now, depending on if you're approaching 0 from the left side or 0 from the right side, you might get positive infinity or negative infinity. Okay? And the opposites are also true. So, like, for example, if you have y equals f of x, the vertical asymptotes of f of x become the zeros of 1 over f of x, and the minima of f of x become the maxima of 1 over f of x. Okay, so like the opposites of all these are also true. If f of x is negative, then 1 over f of x is also negative. If f approaches infinity, then 1 over f approaches 0. Okay? Alright, let's see how this works. I think it's easier to look at an example. Graph on the same set of axes, y equals x plus 3, and the reciprocal function, 1 over x plus 3. Okay, so I'm going to do this one in red, and I'm going to do this one in blue. So first I'll do x plus 3. X plus 3 is a straight line. The y-intercept is 3, and the slope is 1. So it just kind of goes at a 45-degree angle like that, right? Now the blue function, 1 over x plus 3, let's, instead of graphing it by putting in numbers for x, let's try to graph it by using the rules we just stated above. So the red function does not have a vertical asymptote, so that rule doesn't really do anything. Does the red function have a 0? Yes, it does. It has a 0 right here. And the 0 is going to become an asymptote. Interesting. It's an interesting way to find the asymptote. The 0 of the red function becomes an asymptote for the vertical asymptote for the blue function, right? That's what it says here. The local maximum of y equals f of x become the minimum of y equals 1 over f of x. We don't really have a chance to see that because the red function doesn't have a maximum or a minimum. Okay? What about the next one? When f of x is positive, then 1 over f of x is also positive. Okay, that's interesting to know. So that means our reciprocal function is going to be in the region here when red function is positive, and it'll be down here when the red function is negative. Okay? When f of x approaches 0, then 1 over f of x approaches infinity. Okay, and let's see. Let's try to graph based on that. Okay. So we are going to now see what happens when we approach when we approach 0. Okay, so when f of x, which is the red function, when it approaches 0, this point here, the blue function will approach infinity. So it would be kind of like that, kind of like that. Okay? All right. Now let's graph it for real and see how accurate we were. We'll use a dark blue line this time. So let's look at the function, and how do we know how to graph this function? Well, we know that the horizontal asymptote is x equals -3 because that's what makes the denominator 0. And yeah, we have drawn it at x equals -3, so that worked out. What else do we know? We know that the horizontal asymptote is 0 because if you put a big number in for x, you'll just get 0. Okay, so we'll have a horizontal asymptote at y equals 0. And do we have any intercepts? If we put in 0 in for x, that'll give us y equals 1/3, so our intercept would be 1/3. And if we put y equals 0, there's no value of x, which would make the fraction 1/x plus 3 0, so there's no y-intercept. Okay? And last of all, we know that 1/x plus 3 has a vertical stretch of 1, so it's not stretched at all. So it would go through these 2 points, like located 1 to the right and 1 up from the center of the intersection of the asymptotes. So basically it'll look like that. Okay, so our rough sketch was okay, but it was not, as good as we could get by graphing it for real. Okay? Alright, so, but we also, we checked some of those rules and they seem to work. Okay, so let's try this one here. We're going to graph this in red, and then we'll graph this, trying to use the rules above. Okay, so first we're going to draw y equals square root of x. Remember, y equals square root of x is basically a parabola on its side, so we're going to graph 1, 1, 4, 2, 9, 3, okay, and 0, 0. So this is square root of x, okay? And then if we were going to draw the reciprocal function for this, let's follow some of the rules. For example, the reciprocal function says that if the function becomes 0, then the inverse function becomes infinity. Okay, so if I was to draw the reciprocal function becomes infinity. So this would be like an asymptote here. Okay, and what else can we say? The local maximum of the function becomes the local minima of the reciprocal function. So that makes sense because the local minima is here, and the maximum, there's an asymptote here, so it's going up. When the red function is positive, the blue function will also be positive. Okay, I agree with that. When the red function goes to infinity, then the blue function goes to 0. So I would say that they kind of trade places. So the blue function goes down and the red function goes up. Okay. Now let's try to graph the blue function by using some points on, like an XY table. So if we put in 0, of course, that's an illegal value, so we get an asymptote. Okay, I'm not going to put an X, that's confusing. I'll put a line. If we put in a 1, 1 over square root of 1 is just 1. If we put in a 4, 1 over square root of 4 is 1/2. And then if we put in a 9, 1 over square root of 9 is a 3. So let's try to graph these points. We'll graph 1, 1, 4, and 1/2, and 9, 3. So it looks kind of like an exponential function, except it goes up. Actually, it's just going to be a rational function, kind of, okay? So we'll erase our guess, this blue function, light blue function here, and we'll leave the dark blue function, okay? All right. Number 2. Points are points which do not move under transformation. Show that if y equals f of x is transformed to y equals 1 over f of x, invariant points occur at y equals plus or minus 1. So let's look at the 2 graphs that we did here and see where the invariant points occur. And I highlighted them in yellow here. The invariant points are when the red and the dark blue function are the same. When the red point does not change under the transformation. And you can see that indeed both of these points are located at y equals plus 1 and y equals minus 1. So it seems to hold true. Let's look at this one. In this case, there's only one invariant point, and it is indeed located at y equals plus 1. There is no invariant point at y equals negative 1 because this function only has one side. Okay, so let's go back. So actually what we did was we did that first, so that's true. Next thing we're going to do is we're going to look at this, and we're going to try to show that it's true. When we transform y equals f of x to 1 over f of x, it says try to figure out where the invariant points occur. Remember that the invariant points are the shared x and y pairs between f of x and 1 over f of x. So in this case, we're going to compare the two. The x's are equal, the y's are equal. So let's set the y's equal to each other. We'll have f of x equals 1 over f of x, right? We'll put the f of x's together. We're going to multiply both sides by f of x. We'll get f of x squared equals 1. We can take the square root of both sides. We'll get f of x equals plus or minus 1, because both plus 1 squared and minus 1 squared also become positive 1. And I think we're done. Okay, so like when f of x equals plus or minus 1, that's when we get an invariant point, which means that when y is equal to 1 or y equals to negative 1, you will have the invariant point. So we've shown what they wanted. Okay?